We're going to start our last session of the day, and I'm very happy to present Minchen Li from CMU and Jiayi from Stanford. They're going to be talking about physical simulation. So, yeah.
Okay, thanks a lot for the introduction. And hello everyone, I'm Minchen and I'm from CMU. And it is my first time at SGP, and I'm very happy to give a presentation on animation at a geometry processing conference. And today, Eris and I will give you an introduction to optimization time integration for solids and fluids, and a bit more about the speakers. I'm a new assistant professor at CMU, and Jiayi, or Eris, is a PhD student from Stanford University. And today, I will briefly talk about the fundamentals and the big picture of optimization time integration. And Eris will mainly focus on advanced topics based on her recent works. And I would like to start with a more general goal of the general computer graphics, which is to generate realistic visual effects via computing. And this also relates to the three classic research directions of computer graphics. So to generate the visual effects, we first create the geometry or the discretization of our object. And then we assign materials and create rendering algorithms to render the pretty images that are translucent and look very nice. And next, we make it move and create animations. And here, for animation, there are actually multiple ways to create animations. Like in the traditional way of creating animation, artists just draw keyframes of a character, and then the frames in between will be interpolated from the keyframes. And this is like time-consuming, and later on, we invented the skinning technique, in which artists only needs to draw the skeletons, or say place the skeletons or joints, and those joints will control the postures of the character, and then interpolate in between, and the animation of the skin character will be automatically generated, which is more efficient and also convenient for artists. And there's also ways of physics-based animation, which solves the PDE that governs the motions of objects and automatically generate intricate dynamics, including like cloths and rigid bodies and deformable solids and even hairs and fluids. And that's what we will focus on today. And in physics-based animation, actually it incorporates the simulation of multiple phenomena and objects. Like here, in this scene, we have rigid bodies like the ragdoll, and also cloths, and also elastic bodies like the thick rings. And we are also simulating elastic rods represented by polylines as those thin rings. And we could also use physics-based animation to realistically animate the sand and also fluids, including its interactions with cloth. And this character is just the skinny animation created by artists. And there are also many ways to realize physics-based animation. And today, we will focus on one of the techniques, which is the optimization time integration. And it is a reliable simulation approach based on numerical optimization. So I would like to introduce it starting from distortion minimization, since it is deeply related. And it's also where I started before learning animation. And my first geometry paper is about garment animation, and also designing the garments for animation. And my second paper is about parameterization, working with Justin. Yeah. So about distortion minimization, we first want to discretize the space so that we can solve for different different postures for the objects. And here, given a surface mesh of the armadillo we just saw, we can first tetrahedralize it to use tetrahedrons to represent its interior volume. And then for each node, or say vertex of this tetrahedral mesh, we stack all its position vectors together as a long vector here for convenience of the derivation and discussions later. And here we use bold letters for the 3D vectors or matrices associated with like a point in space, and we use regular letters to represent this long stacked vector. So now to measure distortion locally, like when we have two geometries and we want to compare like the map between these two geometry, we want to measure the distortion locally so that we know how to minimize it subject to any like anchor constraints so that we can create mesh editing algorithms. And here, if we look at one tetrahedron element, it is deformed or distorted into another form. And if we assume that the deformation inside this tetrahedron is uniform, then we can quickly write a affine transformation matrix using these vertex positions of the tetrahedron before and after the deformation. And this affine transformation matrix can be used to calculate any map of the point inside this tetrahedron. And once we have this deformation gradient, which is essentially the affine transformation matrix here, we could use it to calculate a measure of distortion. And for example, here, we know that the deformation doesn't include rotation, so any rotation should not be counted as deformation or say penalized. So we could just measure the distance between the deformation gradient to its closest rotation here. And this closest rotation can be obtained by SVD. And this is actually the as rigid as possible, or ARAP energy we are very familiar with. So once we have this distortion measure per tetrahedron locally, we can calculate the distortion measure of the whole body by integrating this local variable, or say discretely we can just take the sum of all the distortion energies per element multiplied by its volume, and then we get the total measure of the distortion, or say the total distortion of this object mapping to any different posture or state. So now, once we know how to measure distortion, then let's say we want to create the animation that we saw in the beginning. For example, we want to like drag its ears like up and drag its feet down, and also drag the waist back. So we just need to minimize the distortion subject to these anchor constraints or positional constraints that we want to fix part of its vertices at a special spatial location. And here, the constraint is just written as a equality constraint with the selection matrix selecting the vertices that we want to fix, and also x hat is just their target positions. And by solving this minimization problem, we'll obtain the configuration where the constraints are satisfied, like the airs are dragged at the top, and the rest of the vertices are like kind of smoothly distributed so that they minimize the distortion energy. So this is distortion minimization, which is very useful for creating different postures or meshes. And here, we could actually just move the anchors to the target position. And we only optimize for the free vertices, which we don't know the positions yet. So in this way, for simplicity and convenience, we could just write it as an unconstrained optimization problem if we have those constraints satisfied and if we don't touch them anymore. So to solve this unconstrained optimization, we could use the Newton's method. And here, essentially, we just want to solve for the critical point of the gradient of this energy. And recall that Newton's method in 1D just start from an initial guess, x0, and then iteratively update the estimate by calculating the derivatives and calculate this quotient and subtract it from the current estimate. And visually, starting from one point here, we just, in 1D, we just calculate its tangent line and find the intersection point between the tangent line and the x-axis. And the intersection point will just be the new estimate of this algorithm. And we can do it again and again until convergence to the root of this function, which is the minimum of the distortion energy. And here, if we want to solve it strictly, we also need to check the Hessian and see whether it's a local minimum or local maximum. But in numerical computation, we usually just go with the root here, and we'll know later why we don't need the second order derivatives checks. So in higher dimension, the update rule for the iterate is similar. Just compute the Hessian matrix or the Jacobian of this gradient and apply its inverse to the gradient and to update the estimate. And the derivation can be based on linearly approximating the function g at the current estimate xi and setting this approximated function to 0. And this will just give us the update rule. So Newton's method can converge very quickly compared to first order methods. But one issue of Newton's method is that it needs to start with an initial guess that's sufficiently close to the solution to converge. Or if we start from a bad initial guess here, the yellow point here, we might like experience overshooting issues where the iterate just gets further and further away from the solution. And this will lead to numerical explosions and generate garbages visually. So to achieve robust distortion minimization, we could equip Newton's method with line search. And here, to look at it again for our problem, we want to solve for the root point of our gradient function. And here, Newton's method can be written in the energy form here by swapping the function g to the gradient of E. So here, for Newton's method, we always take one full step for the update. Like if we understand this negative like Hessian inverse times gradient as a search direction, then we could also consider like taking a fractional step, which can guarantee that the energy won't explode. So that's the idea of line search. And fortunately, there's a theory to guarantee that if P is a descent direction, like the negative of the gradient, then there must be a positive scalar as the step size, that if you taken, the energy will be smaller than the previous one. So that's a good news, and we could take advantage of. So we just need to make sure that the search direction we calculated is descent. So here, we still want to use the second order information in the Hessian to ensure quick convergence. So what we can do is to approximate this Hessian, or say project this Hessian to a nearby SPD or symmetric positive definite form. And in this way, the search direction will also be descent, so that we can perform line search to ensure that in every iteration, we can reach a new configuration with lower energy, and then it won't explode again. So to illustrate it a little bit in 2D, the line search method just find a search direction at each iteration, and then find a step size that decreases energy, and then start another iteration until converging to the local minimum. So to address the previous question a little bit, we don't check the second order derivatives, because with line search, we are trying to find locations with lower energy, and we won't find a local maximum in this way. And also, in numerical computing, because of rounding errors, it's very unlikely we find a saddle point. And actually finding a saddle point is even a harder problem in numerical computing. Yeah. So if we briefly look at the pseudocode of the robust distortion minimization, we first find an initial guess to start with, and then we start the Newton loop by first computing the SPD version of the Hessian matrix, and then compute the search direction, and initialize our step size to 1 to perform the line search to find a point with lower energy. And here, there's another loop that continues when the new energy is larger than the previous energy. And we always halve the step size if this happens until we find a new point where the energy is smaller than this previous energy. And we update this estimate and start over, and until we converge to a sufficiently close point to the local minimum. So this is the robust distortion minimization algorithm. And using this formulation, we could solve a lot of challenging or interesting distortion minimization or mesh editing problems. Like this problem here, we want to just fix the bottom of this rectangle and move the top side to the right. So we get the initial shape here shown in red. And by using the projected Newton method we just introduced, we could obtain a configuration with minimum distortion satisfying both the top edge and bottom edge constraints. And in 3D, for example, this armadillo, if we want to just move its hand to the bottom and get a better initialization, and then we can find the local minimizer as shown bottom right here as a new configuration for this mesh. Okay, so that's distortion minimization. And next, what I want to show is that it's very easy to extend it to optimization time integration for elastodynamics. So recall that we solved the distortion minimization problem by minimizing the distortion energy, and the distortion energy is just the sum of the local distortion measure per element. And here, elastodynamic simulation, like the armadillo slingshot example you saw earlier, is also can also be solved by minimizing a energy, and this energy is very similar to the distortion minimization energy, which is just taking the distortion energy plus another inertia term, which will create the dynamics or inertial effect. And here, this inertia term is actually just a quadratic term, which is easy to deal with. And here, delta t is the time step size, which we'll go over later as we will discretize this time axis to solve multiple configurations in time. And xn is the vertex position at the previous time step, similar for vn, the velocity. And here m is the mass matrix, which is kind of a measure of how large the inertial effect will be. So to get into the details, here with spatial discretization with dynamics, we not only discretize the position variables, we'll only have another discretization of the velocity variable. And this velocity variable is just the velocity of each node stacked together. And once we have this representation that includes dynamics information, we want to discover how to advance it in time, or say solve the governing equations that govern the motion of these objects. And here, this is essentially the conservation of momentum equation, which we need to solve. And in simpler form, it's just Newton's second law. And it just governs the motion of the objects where the force will be integrated to affect velocity, and velocity will be integrated to update positions. And here, the mass matrix, for now, we just take it as a diagonal matrix with its diagonal entries being the mass of each vertex calculated from its incident elements. So right now here, we still have the temporally continuous form. So next, we need to discretize the time into small intervals so that we can calculate the new positions step by step to obtain the dynamics. So to temporally discretize the governing equation, we just need to use numerical differentiation formula to estimate those time derivatives. For example, we could use forward difference to approximate the velocity and acceleration, and this will give us this update rule to calculate the new configurations from the old configurations, which is explicit and very efficient to compute. And alternatively, we could also consider using backward difference instead of forward difference. And if we use backward difference on velocity and forward difference on acceleration, we will get a slightly different form where this velocity used to calculate the new position is the new velocity. But now we still can just first update the velocity and then update the position, which is also very efficient. And we can also consider applying backward difference approximation on both the velocity and acceleration. And then both these velocity and forces used to calculate the new position and velocity becomes the configurations in the new time step. And now we no longer have any explicit formulas that we can directly update these variables. Instead, we have a system of equations to solve, which is an implicit update rule that we need to solve to compute the new configuration. So the question may be that why don't we just use those simpler forms? So the answer is that they have different stability properties. So if we use this uniform circular motion as a testing example and run different time integration methods on it, we find that for Euler will just explode with very small time step size. And the symplectic Euler formula, which uses both forward and backward difference, will be stable and be very accurate because it's symplectic. And the issue here is that symplectic Euler can only be stable when we use a relatively small time step size. And here on the rightmost, we have the implicit Euler time integrator, which will have a large numerical dissipation that damps the motion to static at the end, no matter how small time step size you use. So here, we choose the implicit Euler for creating lots of animations in graphics because it is unconditionally stable. And even if it introduces damping, the animations still also needs damping, right? So it's kind of compensate that we sometimes don't need to additionally model damping. So that's why we choose this implicit Euler formula that can maintain stability but requires expensive nonlinear system solves. So similarly, to solve the Bracco-Euler nonlinear system, we could apply Newton's method, which is similar to distortion minimization. And we still have the overshooting issues, which leads to simulation explosion. So instead, we convert it to an optimization problem by integrating the force with respect to the world space or say new positions so that we have the potential energy whose gradient will give us the negative of the forces. And then we have this energy to minimize where at the local minimum of this energy, the implicit Euler update rule is satisfied. So solving this optimization problem is equivalent to solving this nonlinear system. And then we could apply our projecting Newton method with line search to minimize this energy and guarantee convergence and find the result with unconditional stability. And here, algorithm 2 is just the backtracking line search that we previously discussed. So now we've covered the distortion minimization, and we've seen how to extend it to elastodynamic simulation. And next, we will see a case study on implementing a 2D easy system of simulating the elastodynamics effect. Yeah, questions?
On the previous slide,
Yeah.
where is the velocity used again in this case?
Oh, yeah, that's a good question. Thank you. So here the velocity is actually eliminated from the formula because velocity is dependent on the position variables. So we only solve for the new position variables and then update the velocity at the end. Yeah, this.
And how is the velocity used?
Oh, velocity is used to velocity is used in the inertia term to calculate the here. So velocity is used here to calculate the x tilde, and x tilde is used in the inertia term. So it's kind of predicting one possible position such that driving the positions close to it will create inertia effects. Yeah. Okay. So having going through the fundamentals of the elastodynamic simulation, next we can see some practical stuff where we implement one simple system using Python in 2D. So we'll look at this easier setting of mass spring system, which we initially stretch a square and release it to simulate its elastodynamics. And here we can see some vibrations of this cube until it's becoming static. So here we are introducing another slightly different but easier model for modeling the elasticity of solids using springs per pair of points. So here we just first create a square or say a matrix of points and then use edges to connect them per row, per column, and also per diagonal. And here, each edge will be represented as a spring, which if you stretch it, it will exert like forces to drive the length to the original length. And here, once we have this mesh, the next step is just to implement our implicit Euler update rule, which is equivalent to solving this minimization problem. And here we have the inertia term, the elasticity energy, and in this case, it will be written in the mass spring system form. And here the energy we are minimizing is called incremental potential. So essentially, we just need to implement this algorithm with Newton's method to solve for the solution and then update velocity. And here, the critical parts would be to implement the calculation of this energy value gradient and Hessian, and the other parts are just can be implemented with direct translation from the pseudocode to Python or other languages. So we can look at the energy terms one by one. So for the inertia term, it's a simple quadratic energy, so it will be easy to calculate its gradient and Hessian. And here, note that the mass matrix is already SPD because it's a diagonal matrix with positive diagonal entries. And calculating this energy value is straightforward. We just loop over the vertex and then follow the expressions to calculate per vertex energy and then sum them up. And similarly for the gradient, where we need to create a stacked vector for the gradient and store the gradient to the corresponding entries. And here for Hessian, we use a sparse matrix data structure to fill in the diagonal entries, and we also loop over the vertices. So next, for the mass spring energy, recall that in 1D, the Hooke's law defines the elasticity energy of a spring as the 1/2 of its stiffness, K, times the spring displacement squared. And in higher dimension, it's actually very similar, or say easy to extend. We can still calculate the current length of the 2 points using their current positions, and then minus the rest length to calculate the delta x, the spring displacement, and square it to calculate the energy. Or we could also just write it in another form where we divide its current length with its rest length and -1 to kind of create a stream measure where 0 means no deformation, and deformation will just increase as the string value increases. And here, for this case study, to avoid computing square root and taking differentiations, we could just use the squared length to create the stream measure. And it's still valid, and it will be easier to calculate the gradient and Hessians. And here, since it's in the continuous setting, we actually need to calculate the integral of the energy over the space. So here, the L square can actually be understood as a area weighting. And this later term is the elasticity energy density term, which is the elasticity energy per unit area. So based on this form, we can easily derive its gradient and Hessian because we don't need to care about the square root anymore. And once we have this formula, we could similarly just traverse all the edges and calculate their energy and add them together. And for gradient, here we need to make sure that these gradients are added to the corresponding node positions. And for Hessian matrix, we also use the sparse matrix data structure. But note that here, the Hessian of this mass spring energy is not SPD anymore. And we need to project it to a positive definite form. And here, to do this, we actually project it per edge so that we have a smaller matrix to project rather than a very large matrix to project to SPD, which will be very expensive. And projecting it locally also approximate the Hessian matrix nicely because it's because there is still second order informations remains. And the projection can also be formulated as minimizing the difference between the new matrix and the original Hessian matrix, subject to that the new matrix is SPD, right? And based on eigen decomposition, the problem can also be can actually be solved by just zeroing out the eigenvalue, the negative eigenvalues, and reconstruct the matrix. And here we could easily implement this algorithm. And in elastodynamics, because the mass matrix has positive diagonal entries, so here we only need to modify this elasticity Hessian to a positive semi-definite form, and then add it with mass matrix, the whole Hessian will still be SPD. So we don't need any epsilon here to add to the eigenvalues. So now we have the energy gradient and Hessian of the two terms, and we just need to add it together and implement this time integration algorithm with the Newton's method for solving the nonlinear problem. And this is also just a straightforward translation from pseudocode to Python. And now, once we have the time integrator, we can write the simulator code here, just initialize the material parameters like time step size, stiffness, and also allocate the memory for the variables like positions, velocities, and mass matrix, and then set up a simple rendering system and call the advanced time step and rendering in every time step. So this can be implemented very efficiently with just 6 Python files, with each with like hundreds of lines of code, like less than 100 lines of code. And for a quick demo, the program just gives us this like initially stretched square simulation. And here we could also change its discretization to have more points, and it gets slower but have more details. And if you implement it in C++ carefully, it won't be that slow. It's because I'm not a very good Python programmer. And here, we have released this code as a simple tutorial for solid simulation online. And there are multiple like tutorials, each in one folder, including contact, friction, and also inversion-free elasticity with Neo-Hookean energy. And we also released a free online book on physics-based simulation, and currently start with only the content for dynamic contact simulation. So if you are interested, you can take a look, and you are also welcome to contribute to our free open source online book. And here for the Python tutorial, a good news is that a GPU version is coming, so we can expect to see like high performance, easy to read, organized code for introduction to optimization time integration. Okay, so the last part of my talk for the first part of this course today is more topics on optimization time integration, because it not only enables robust and accurate elastodynamic simulation, but also gets extended to simulating more phenomena and effects. And first, we will see that it can be extended to simulate self-contact, where we handle the contact between different regions of elastic body, or say multiple elastic bodies when they are deforming and moving. And here, we are still solving this minimization problem, but subject to a inequality constraints that asks that every non-adjacent surface primitive pairs on this surface will have a distance that's positive all throughout the simulation period. So with this formulation, we can still solve the minimization problem with constraints to simulate this self-contact effect. And here, we are actually converting it to an unconstrained problem by using barrier method, which where the barrier function will goes to infinity when the distance is getting 0, and it smoothly decreases to 0 when the distance gets larger. So here, the threshold d hat here controls the compactness of the function, and if the threshold gets smaller and smaller, then this simulation will be more accurate to the discontinuous phenomena of contact. And here, we could also, based on this optimization time integration framework, to simulate thin objects like cloth. And we are still solving the same problem, but with slightly different string energies defined especially for cloth. And here, since the cloth is very thin, we just use a triangle mesh or surface mesh to simulate cloth. So we actually model the stretch component of the elasticity in the tangent space and the bending component of the elasticity separately. So here, the stretch is just the stretch just measures the deformations in the tangent space, and this is only intrinsic. So we also model the extrinsic component where we measure the bending angles, dihedral angles per triangle pair, adjacent triangle pairs, and the energy is modeled to penalize the difference between this angle in the current configuration and the rest shape of the cloth. So in this way, we could simulate clause in this optimization time integration framework, and we could generate great animation results with the accurately resolved friction, where we see the table clause pull example. If we pull quickly, then the objects will be left on the table. But if we pull it slowly, it will be like the trick will be failed. And here we are coupling clause simulation with elastic bodies and also nearly rigid bodies like the bottle and the cup. And here, for nearly rigid bodies, if we don't care about the tiny deformations or say the fast vibrations, we could also just track the rotation and affine transformation and the translation per object. And then we have much less degree of freedoms to solve in the system. So here, for this object with the center of mass and an arbitrary point, if we track the rotation or affine transformation Q and also the translation little q, we could resolve any resolve the new position of any material space positions on the original mesh in this form. And this will result in constant deformation gradient per body. And we could simulate this reduced system also by solving the same optimization problem, but we only solve it in the subspace, where the subspace is parameterized by the big Q and little q here. And in this way, we could simulate rigid body effects in a robust and efficient way, like this wrecking ball and gear set. And actually, we could also use optimization time integration to simulate fluids. And here, we're also solving the same problem, but the energy will definitely be different. For example, we can define the distortion energy as only measure the volume change of this material, so that we don't penalize any shearing motion, so that fluids can flow around. And here, we may not use meshes because there will be like complex remeshing operations. So instead, we could consider using purely particles and use meshless method like SPH or MLS to estimate the local deformation gradient at each particle, so that we can calculate their forces and then simulate fluids. And here, this clause fluid interaction demo is simulated in the previous formula. So to conclude, we have a brief introduction to optimization time integration, which enables reliable and versatile physics-based simulation by this unified framework. And there are many meaningful future works going ahead. So first of all, we are still using the Newton's method to solve this problem, or say we need to solve a nonlinear system. So if we have a large number of degree of freedoms, then efficiency will be a big issue. So improving the efficiency and scalability of the solving process of the nonlinear problem will be a very meaningful direction. And secondly, the elasticity effect is actually a conservative effect, which is not path dependent, so that it has a potential energy that we can use in the optimization form. But for path-dependent effects like damping, plasticity, and friction, which doesn't have a well-defined potential energy, then it is tricky to incorporate them into the optimization framework. And recently, we have some explorations in this direction, but it's still not perfect, and it's still a meaningful future direction. And lastly, applying the optimization time integration to inverse problems like computational design and robot learning will definitely also be very meaningful. And nowadays, we already see many existing works trying to use our robust and efficient solver in their like reconstruction or computational design and exploration tasks. So that's the first part of this course. And I would like to thank you, and maybe I can take 1 or 2 questions, and then we can invite Eris to present the second part. Yeah. Thank you.
In one of the slides, you have a picture or animation of sort of the claw simulation over a sphere.
Yeah.
And at the very bottom, like, it sort of very nicely folds over itself. And there are like no self intersections, but I don't see like any like penalty term against that in the energy. Is that like ever an issue during this optimization, or is that somehow accounted for?
Oh yeah. So in this example I'm showing, is actually including the barrier term for contact, which I didn't wrote in the previous slides. In the previous slides, I only wrote the elasticity component of this clause. And for extending to different phenomena, we could always just model them using potential energies, or say approximating one kind of potential energy, which will give us the force of that phenomena, and we can incorporate it into the optimization framework.
I see.
Yeah.
Thank you.
Yeah. Okay. If no questions, we can welcome Jiayi to present the second part.
All right, so thank you, Minchen, for the nice presentation. And hello, everybody. I'm Eris. I'm currently a PhD student at Stanford University, advised by Professor Doug James. And today it's my great pleasure to talk about like the second part of this course. And also, yeah, I think I'm so happy to be SGP, just because although nowadays I'm mainly working on simulation stuff, I also kind of consider at least half of myself as a geometry person, just because I did my undergrad at the University of Toronto, and I was working closely with Professor Alex Jacobson there. And I think lots of my knowledge in this area actually started from geometry processing stuff as well. Okay, so in the second part of this course, I guess I will focus more on extending like this fundamental optimization time integration framework that Minchen just introduced, and also how we can actually develop tools that can both be usable and controllable for artists and designers based on that. And this topic is actually something closely related to my own research since I was an undergrad, but also I will mention a few other representative work kind of like done in this area by other people throughout this talk. Okay, so let's jump right in. So hopefully, after the first part of the course, you guys at least agree with me, like physics is supposed to be our friend in many use cases and applications, like animation, design, and content creation related tasks. And this is pretty natural, it's just because physics explains the fundamental principles governing the behavior of the natural world. And this is perhaps one of my favorite demos, which was released at Adobe Max 2020 Sneak to further kind of illustrate this concept. And in this thing, you can say the artist is trying to set up a design layout in a virtual space by directly manipulating the objects, much like what we do in the real world. And the reason why it feels so smooth and effortless is actually all because the incorporation of physics. However, surprisingly, when you actually speak with artists, they often express like significant frustration with these simulation tools. Like for example, even with such a simple setup, achieving like the exact motion desired for a basic character still involves like a significant amount of manual work from artists to ensure like all the details just looks correct to them. Let alone like more complex things involving different materials, detailed geometries, deformation, and also context among numerous objects. So one reason, or at least I think a major contributing factor why artists continue to be frustrated with simulation tools is just because solving the equation of motion based on initial conditions is inherently like a forward process. And that said, even though the simulators we as researchers are developing today are getting more and more accurate and also robust, they still remain essentially like forward processes that operate autonomously. And this means this is basically there's basically no room for artist control or intentionality during like the forward simulation process. So to be more specific, one naive approach, like we can directly leveraging direct simulation to assist artists, involves generating like numerous samples, crossing your fingers, and then hopefully like you'll be able to efficiently select one that meets the artist's needs. However, this is still often the case that no single sample fully satisfies like all the animator's requirements. And additionally, this method is just not scalable for high fidelity fun simulation that require extensive computational resources. So what artists really want should be art-directable simulation instead. So in line with this philosophy, the first work I'm going to introduce is called complementary dynamics, where our aim is to exactly bringing artists and physics to work in harmony. So when it comes to realistic character animation, there has been these existing principles, and specifically in this work, we were focusing on identifying the right relationship between primary and secondary motion. And to be more concrete, if you compare, say, like the left-hand side and right-hand side of these two animations, you will notice the primary motion just means like the cat's overall body movement, which is a jumping motion. And the secondary motion just means like the wiggles and jiggles, including the natural follow-through of like the cat's ears and whiskers. And to create the primary motion, usually people will use a technique called skinning. I think like maybe the geometry people are pretty familiar with it here. And then after that, there's another technique kind of like called like keyframe animation based on that. And then the animators can just set like the anchor points along the time axis and then do interpolation in between to get like the in-between motion. However, when leveraging physics to assist the artists in their creative work, we observe that existing methods somehow put these two roles on a false linear spectrum, which means like, for example, in one type of method, which is called rig space physics, the basic idea is basically say, okay, we're using a subspace which is parameterized by the rig or say the original primary motion, and then just solve for physics inside that space. But the downside of doing so is like, for example, with like this hedgehog, if you want to say detailed movements of each individual spikes on the hedgehog's body, you kind of have to just put so many additional handles to expand the original rig space. So this can be additional redundant work for the artist to manually do to incorporate physics into it. And instead, we advocate that creative primary effects and physical secondary effects are not contradictory, but rather they should be complementary. We are going to show like this observation is not just true conceptually, but also philosophically and also algebraically, such that the animation artists can use low-dimensional rigs to control the primary motion, and also rely on our complementary dynamics framework to add interesting elastodynamic secondary effects. So here, to explain a bit more about the underlying method, the input to our method is like a generalized rig function, which can be literally arbitrary, ranging from like linear rigs to nonlinear rigs like dual quaternion skinnings or even wire-based deformers. And as a result, agnostic to rig types, we generally treat them just as like a mapping from some low-dimensional control parameters to match vertex positions, which is a full space. And meanwhile, we treat artist's input as a sequence of such like rig parameters, and at each frame t, our key ideas is to kind of just add the secondary motion on top of the original rig-based displacements. Or in other words, I think the thing we want to do is to break the true displacement that we're gonna solve for in the physics-based optimization framework into two parts. And based on that, if you again look at the energy formulation, all we need to do is to just change the variable. And this is essentially the same energy formulation as Minchen just represented, with both the elastic potential term and also the inertial term. Yeah, and here we just, swap in the new variable. However, if you bluntly solve this unconstrained minimization problem with a new variable, the physics is so aggressive such that it will completely undo the rig pose as is illustrated here. And the key idea we developed in this work is to instead constrain the complementary displacement, which is a UC, to only those displacements that could not be created by the original rig. Mathematically speaking, given the current rig parameter PT, we can then verify any candidate displacement UC satisfies the criterion by ensuring that projecting to the closest rig displacement simply recovers the original PT. And here, although I guess I don't have enough time to go into the simplification details, but the thing I want to highlight is just like this scary mathematical form can actually be nicely simplified as this single linear constraint. And as a result, at each time frame t, we compute the local tangent space and then just restricts the complementary displacement UC to only live in the space orthogonal to that. And because of doing this, the original unconstrained optimization system now just becomes like a constraint one subject to a linear constraint. Yeah, and you can just simply write down the new formulation here. And as some results, you can say the input will just be the artist's rig animation. And on the right-hand side, it will just now become like very mimic, like after adding the physical secondary effects. And also, I guess, apart from solids, we also kind of like can use our method to cloud simulation. And this one is actually just using the super basic material model, which is a mass spring system that Minchen just introduced as a case study. And here we can show like this carpet is actually only rigged with 2 handles, which is super simple. And by adding the complementary part, it's actually, already looking pretty good. And also the same is true for like rigid body simulations. We could similarly like add secondary effects to post-process like a rigid body simulation and make it look more elastic without needing to rerun the whole collision detection process or change like the overall scattering of the objects. All right. So up to here, I think I'm only describing like the original kind of like full space framework of complementary dynamics. But I think you may notice, since it's still kind of like just solving for the displacements in the full space, it can be super expensive because like the cost rapidly increases with the mesh resolution. And also it's worth to mention that although we can only apply like a linear constraint, like the J matrix, which is like the first order derivative of the rig function, is actually like a dense matrix. So when you're actually now solving the constraint system, it also gets more expensive. It's just because of like this super thin but dense part. Okay, so I think it's just like generally true to pretty much all the simulation methods. I think another goal of us is to speed up this so it can be used for more broad applications, especially those ones like in real time. So similarly, like as Minchen just mentioned, like in the nearly rigid body work, we do the change of variable here, where the key ideas is to just like replace the full space variable with like subspace parameterization. And here, I think the specific dimension, or say the representation of the subspace we pick here, needs to be super small. So later, when you actually expand the equation and rewrite the whole formulas, it can end up with being like a super small linear system that is fast to compute. And also, I guess in this follow-up work, we also kind of like find a nice way to get rid of the linear constraint. So it's already baked in the subspace we choose. Yeah. And now with this new fast version, it's already like 100 times faster. And also, one thing I want to highlight is just in this work, we also present like a new subspace representation, which is called scaling eigenmodes. And it has some like nice properties, which is rotation equivariant. And I encourage you to actually look at the paper to learn more details. Yeah, and they just add some results. Now, beyond just one single golden fish, we can simulate like the whole aquarium with more than 1 million tetrahedra in real time. And then I think complementary has become super useful in many of these kind of real-time applications, like for example, face tracking augmentation, and also skeleton tracking augmentation. Okay, so I think, however, like in physical simulation, also I think in the previous work, we kind of like really push for the speed in that specific application. But I think in physical simulation in general, there's still always this fundamental trade-off between speed and fidelity, which means like I think in the long term, we definitely want our simulator to be both robust, accurate, and also runs really, really fast. So it satisfies basically all the needs in our daily life. But I think in the short term, there's just no free lunch. And this is mainly because also, say, like the high-speed methods for cloud simulation, for example, are now reaching interactive rates for extreme-scale cloud meshes. Due to the simplification and also the limiting assumptions made in the simulation model, its expressiveness is still largely restricted. I think like as an example, in fast complementary dynamics, using a subspace still kind of like reduce some amount of like the wiggles and jiggles. And even worse, in some context-rich scenarios, the simulator can just be incredibly unstable and sometimes generates undesirable creasing and intersection artifacts too. On the other hand, I think, as Minchen just presented, high-fidelity methods like IPC are growing increasingly expressive with simulation results that closely mimic and even in some cases accurately depict the world around us. But in general, they're still just far away from reaching the interactive rate. But is it really impossible to get the best of both worlds? Here, we want to get the beautiful and realistic folds, wrinkles, and contexts that those high-fidelity methods provide with us while still giving interactivity to the users. And most immediately, we're looking at how to enable interactive exploration for class design parameters. Okay, so to develop such a solution, essentially here we're inspired by the success of progressive refinement strategies in rendering and also some of those early geometry processing work from both of those, I think, kind of old one and also some new advances these days. It sounds like a natural fit to class simulation, it's just because wrinkles and folds could similarly have different levels of details. But the question we are facing is how we can actually extend progressive methods to class simulation. Well, to enable the progressive simulation, there are a number of challenges that we'll have to overcome. So one obvious approach is to design a scene using very coarse-res interactive simulation. And then once all material and layout parameters are finalized, finish up with a finer resolution mesh. But this immediately runs into trouble. It's just because you could say, like, for example, part of the fine sheet got stuck on the armadillo's nose. Moreover, I think it's just because like the low res and high res wrinkle pattern kind of do not match with each other. And alternately, I think we can also try cascading the simulations. That is, warm starting each finer simulation solve from the last one. But this also doesn't work. It's just because mesh-based class simulation, sorry, it goes too fast. Yeah, because it's just because mesh-based class simulation suffers from the known membrane locking issue if using a too-coarse geometry, and the fun-level simulation will exhibit all these sharp creases and also kinks all the way up, which means like those artifacts will just always be there at your final high-res output. Lastly, also linear multigrid similarly maintains a hierarchical structure. We can't just apply linear multigrid to solve our overall progressive problem. And the main reason is just like the ultimate goal of multigrid as an iterative solver is to make the finest level linear solve faster. But the coarser level in between solutions are neither meaningful to visualize nor ensuring any consistency. So it's orthogonal or say complementary to our goal, and designing a multigrid solver to accelerate IPC is an interesting future work. So to achieve both a high quality and interactive simulation, we propose progressive class simulation instead. And this is like a new forward simulation method for efficient preview of class quasi-statics on exceedingly coarse geometries with consistency, reliability, interruptibility, and also interactivity. And I think as a simple demo to demonstrate this, you can say actually this application, this app supports like a few different types of interaction. And you can say the mesh geometry rapidly refines when there is no user interaction. And for collision resolution, it gives like this asynchronized responses, so the class will gradually catches up as the collider moves around. And following that, users could also just plug in real-world material parameters and changes them on the fly. And this is all because IPC is like an accurate method, so we can just grab like the real-world parameters and plug into it to get it to use. Or even attach some handles to manipulate the class. And when all is starting to look good, do some local fine-tuning. And in the end, like after a few progressive refinement steps, you can just send like this converged fine geometry to some fine production level renderer and get these beautiful final drips of fine wrinkles and details. And regarding how we actually get from like the initial state to the final converged shape, like many other physics-based simulation methods, I think our objective as a finest level is always kind of like this incremental potential problem as like the first part of the course just introduced, which is this variational form. I think everybody should be already pretty familiar with it. And specifically, I think in this work, the objective E could be further broken into two parts, which is the elastic part and also the contact-related potentials. I think someone just asked about this question before. Actually, I think in this one, because it's based on IPC, we also have this like contact friction and also other strain limiting barriers to enforce those non-interpenetration constraints. Yeah. And build on this, after some optimization steps, the state will converge to a local minimum of the energy, where each local minimum just corresponds to an equilibrium state. Okay, since we are facing this multi-resolution problem, For each piece of the deformable class, we also maintain like a mesh hierarchy from level 0 to level L with increasing resolution, where the number of levels to use is up to like the user's choice, so it's pre-computed. And inspired by the multigrid methods, as I just mentioned, depending on the way the hierarchy is constructed, we also construct like a corresponding prolongation operator to transfer information between different levels. And here, I think as a specific instance, we use modified loop subdivision, which preserves boundary like as a default choice. And following that, it just for each level, a corresponding incremental potential problem can be similarly constructed based on the mesh discretization. And also each local minimum of this per level energy corresponds to like a converged state at this level. And since in this work, we're dealing with quasi-statics specifically, we actually don't have like a real-time access as in the dynamic applications, but still we kind of like apply like a similar strategy, and we call it artificial time stepping. But you can understand as like the goal here is just to say getting faster and also more robustly to the local minimum of the original elastic energy and also the contact potentials. Okay, and the core idea of this work is just to say, instead of using the original elastic energies at per level, we do this parameterization. And we're also just taking advantage of the prolongation operator, as I mentioned earlier. So here, PI can be pre-computed and directly prolong information from the current level to the finest level. And similar to the original incremental potential problem, we again break like this new energy F into two parts, like the barrier part and also for handling contact strain, and also the elastic part to get the deformations and wrinkles. But here, as I mentioned, I think the smart thing we do is just instead of using the per level one, we now do this parameterization. So the elastic energy is always computed as a fun level. And we use like the coarse mesh or the coarse structure as a subspace, and then just prolong like all the states to the finest level. But still, like the degrees of freedoms are the coarse level ones. So you're solving like a smaller system there. Okay, and similarly, after a couple of optimization steps, it also just converts to a local minimum under specific like user inputs and other time varying conditions. Yeah, and it's also worth to mention that besides like the elastic parameterization part in this work, because we think like our goal is to always prevent interpenetration from happening at all levels. There's also this like safe initialization step, which is gonna happen, say, when you actually want to go from the current level to the next level. Due to time reason, I guess I won't explain all the detail here, but I think I just want to mention that I think we use CCD techniques to find like the biggest step that the search can take to get to a closest interpenetration-free state when you are doing this upsampling operation. And also for the string limiting constraints, apply like another optimization to get all the principal stretches to be under the original limits specified by the user. And having all this together, we can now showcase like a creative workflow enabled by progressive cloud simulation and also the interactive tool we build upon it. Yeah, like you can say in this rainbow twisting one, we could say PCS enables like handle-based clause manipulation with contact to interactively twist clause against itself, and also rapidly forming like this complex and also tightly wound geometries from the very simple input shapes. And this is also like a fancy final render for the final outputs. And this is a still life example where the user is trying to set up a table class. And you can see with PCS robust collision processing, users can also just directly apply transformations to the complex collision objects to intuitively push class around and also between those different shapes. And as equilibrium is reached for edits, PCS just automatically starts the progressive simulation to finer level solutions. Yeah, and just when no further edits are desired, the user could just maybe go to grab a coffee and also a couple of minutes later come back for this converged high quality and non-intersecting results for the tightly nested and complex geometries. Okay, so far we have talked about class. However, like a fundamental limitation to this first version of the progressive simulation techniques lies in its reliance on a hierarchy of meshes created through loop subdivision. And this is kind of okay for class, it's just because it always presents like a flat surface for the raster shape. But for shells, or say curved surface in general, this can be a big issue, which is simply because any surface that is not representable by repeated loop subdivision of a base mesh, like either with this complex boundary or the intricate built-in details, can just not be simulated. And meanwhile, the collision geometry will have to be treated separately because it's not in the same unified domain, because previously we have to separate the flat part from the curved parts. So to address these limitations, we also kind of like publish a follow-up work, which is called Progressive Shell Quasi-Statics, to extend progressive simulation to support the high-fidelity modeling and design of all input shell geometries with unstructured triangle meshes. And the key idea here is like given an arbitrary triangulated input model, our algorithm will just first construct the hierarchy in a fine to coarse manner and correspondingly build a tailored prolongation operator specifically designed for shells. And this is just to echo like the previous two key points in the first progressive simulation work. I think in this follow-up one, I think the key modification we did is on the one hand, because now we're dealing with shells, we need a smarter prolongation operator that can handle curved surface other than just naive loop subdivision. And also on the other hand, safe initialization, or say the safe app sampling part is getting harder. It's just because now you don't have like a fixed topology to operate on. It's just because all the simplification or say the mesh coarsening steps are computed like in a fine to coarse manner. So you get to keep track of all those edge collapses and then reverse those operations when you're doing app sampling afterwards. And also, I think like for the prolongation part, I think I want to mention like the operator we ended up with using is actually based on this one, which is called intrinsic prolongation. So I think this is a collaborative work I did with Derek, who is now at Roblox Research now, in the space of geometry processing. Because back then we were trying to just kind of like do linear multi-grid for the linear systems. But I think like I think the cool part here is just like we build upon it such that it can handle like the nonlinear optimization in the simulation applications now. And I think it's like kind of like a good example to show like there are many cases where geometry and the simulation can share things in common. Okay, and also again, as some examples to show, in this balloon inflation one, the quasi-static simulation first runs as a core scale to provide the user with a preview And once it converges, automatically refines all the way to the finest level with fine-scale simulation details being progressively added. Also, because now we can handle curved surface, like in a unified domain, we don't need to special case the collision objects anymore. So now the progressive simulation, like in this example, is just some like sleepy shell characters resting inside a rigid shape. And here, both the collider and the blown-like characters are modeled using unstructured meshes, which are simulated like all together post-Mellon artist and then progressively refined. Okay, so far, we have only talked about quasi-statics, but actually in animation or dynamic simulation, rapid design of high-fidelity fine simulation has been a long-standing challenge. And as an example, for anybody who have been using Houdini, you might know this like vellum solver. And we never say if you use like a coarse mesh to generate like an animation you like, and then just takes the same parameters using a finer mesh, you will immediately realize like all the nasty animation you just get won't work in this setting anymore. But all the change you do is actually basically just the mesh itself. And here's like a more extreme case where you get like this ugly stretching artifacts. Okay. So this motivates us to think about how to generalize from quasi-statics to dynamics. And this year at SIGGRAPH 2024, we also have like a work which is called progressive dynamics. And now you can say, once the animator gets something they like at the courses level, we can similarly get progressively refined all the way to the finest, but you can get all this nice detail being progressively added while ensuring like your course preview outputs are always of high quality. So it's something that you can visualize before you get the final converged solution. And this is just another view of the same animation. Yeah, and also we actually get pretty cool results, but due to time reason, probably won't have time to go through them now here. But yeah, we'll be pretty happy if you can come to our SIGGRAPH talks this year. Okay, and besides progressive simulation, I think in the end, I also want to briefly mention like maybe some other alternatives to better address like this fundamental trade-off between simulation speed and fidelity could be, for example, adding some adaptivity to the simulation framework so there's like a more efficient use of the degrees of freedoms at the runtime instead of, I think, in progressive simulation right now, like the whole hierarchy is pre-computed. So you don't, like the user don't have room to like change them like on the fly. Okay, so in the end, as a quick summary, I think we show how various recent advances in elastic dynamic simulation are rooted like in a shared optimization time integration framework that Minchen just introduced, and also incorporate like art directability. And also to incorporate art directability, this framework actually already readily supports all kinds of extensions like subspace methods for faster simulation, enhancement to rig-based animation with physical secondary motion, and also in the integration of multi-level methods for rapid previews and enhance the user interactivity among many other exciting applications. And I personally do believe like there is still lots of room for future research to better address all these practical issues regarding like the accuracy, robustness, efficiency, and controllability of elastodynamic simulation. And yeah, so we can better leverage physics to build tools for creative artistic work. Okay, thank you, and also I'm happy to take any questions.
Yeah, we have a few minutes for questions. surfaces?
Oh, yeah,
Just because
sure.
I kind of like, I imagine like the cloth takes on like a curved shape under like simulation.
Uh-huh.
So I think I was just a little.
Okay, yeah, actually that's a great question. And actually, let me go back to the slide. Yeah, serves as our original motivation to do the shell work. It's just because I think originally we kind of have a coarse, flat cloth mesh first, and then just you can do subdivision to get a finer res version, right? But I think for shells or curved surface in general, I think in many cases, like the original model that the simulator get from the artist is already like a super highly detailed one, which means like in that case, you can't just say, okay, grab it, use it as a coarse one, and then subdivide it to get a final version, because it's already pretty dense, you know. So I think this motivates us to reverse like the way we construct the hierarchy. So to go from fine to coarse, or in other words, we need to somehow build a proxy or surrogate model for the original fine input.
So I have a question about the secondary motion being added after the initial animation from the artist on the example with the fish. So regarding those complementary dynamics, are there any constraints that come into the model before the secondary animation being added? Like, does it take like the bone structure in consideration, whether to keep that animation and those part of the bodies and just deform the rest? Or are there any controls or any restraints being added so the model knows what to adjust and what to keep from the original animation?
Right. Actually, that's a great question. I think we're assuming like the inputs to the complementary dynamics framework will be, for example, like a skinning mesh, which is the surface one, and also the rig associated with it. And on top of that, we will construct like a tat mesh, and usually it's like embedded the original skinning one. And also, I think we are assuming here, like by getting that rig, we know the mapping from like that low dimensional space to the rig space, you know, but it can either be linear or not, but we somehow at least need to know what that function is, and then compute the gradient matrix to use for the constraints. Yeah, so I think like generally, if it's for the practical use, when the rig gets like really, really complex, or somehow you can't get that function, I think it is still like a limitation or something like worth further investigation.
I just want to say that was awesome. I really enjoyed it.
Thank you, Rohan.
Hi, when you go from the lower resolution mesh to the high resolution mesh, how do you take into account that the transition might cause penetrations to appear?
Oh,
And-
I see. You mean the progressive stuff, right?
Yes.
Yeah, okay. Yeah. Okay, I guess this is my bad, because I think I was too brief, like regarding the details here. So actually, I think like how the method works is like, okay, you first take your simulation steps to solve the optimization problem at the course level. And once it converges, which means like you get like a converged preview shape at the course level, then you need to somehow go to the next level, right? As that step, for example, if you're using loop subdivision, you can just say insert all the finer level vertices just by subdivide or say upsample the original coarse triangles, right? But the issue with that is just say it can potentially violate like the string limit constraints, which are pretty common actually for cloth simulation. So here we actually apply like a separate optimization step to get all those parts fixed. But for cloth specifically, I think the interpenetration part is not too hard to handle. I think the harder part is gonna come in from the shell version. But yeah, but I guess I just didn't really touch any details regarding that. So.
Right. So for your collisions, do you do vertex to triangle, or do you do edge-to-edge collisions?
You mean, do I do all the changes for all the primitive pairs, or?
Right. I mean, because I'm still thinking that, maybe I'm misunderstanding, but changing the resolution of the mesh might introduce artifacts of, like, a vertex poking through a smaller triangle where it wouldn't be poking through a larger triangle.
I think maybe this is a good illustration. You can say for the upsampling part, first step we did is just say insert those missing vertices from the fun level, right? And this is purely implant, right? And they won't have any interpenetration issue, but the issue will possibly be, for example, as I said, like the triangles might not be under the previously specified like principal stretches limits, and that would be the actual trouble we're gonna running into later. So you also need this extra post-processing step.
Okay.
Yeah, maybe we can finish here for today. Certainly, people are welcome to linger and ask questions offline. But yeah, thank you very much for coming. It was a great day.